Okay, so today we're going to talk about interference patterns, and there are three primary ones you need to know: constructive, destructive, and mixed interference. This should be a little familiar to you. I believe you talked about it in physics last year. And basically, it occurs when waves come together. We say a collision of two or more waves, at least that's what the book says. That implies they're hitting each other face on. They're frequently drawn that way, but it can also be when wave trains of different speeds move in the same direction and they just happen to catch up with each other. So for constructive interference, it's wave trains that are in phase, meaning the crests add to the crests and the troughs add to the troughs. So what this does is it increases size. Out of phase means that crest goes to trough and trough goes to crest on the wave train, which means that it makes it smaller. The most common, though, is mixed interference, which is where you get swells that come together that have different wavelengths and different periods and heights frequently. If you take out your book and you look at figure 8.14, there's three pictures. I'll show it again at the end of this next few slides. It sort of shows them as an addition problem. And you get a height that is the sum of each individual wave height. So if you have, they're coming together in phase, and you have a height that is, say, 2 meters on one wave and 3 meters on the other wave, if they're perfectly in phase, when the crest comes to the crest, it will be 5 meters. And you can see why this might be some of the more dangerous waves. For destructive interference, they come together perfectly out of phase, which means trough to crest or crest to trough. And if their heights are the same, this actually cancels out. I believe Mr. V used to show a with a sound wave, one that had the exact same amplitude as another, and he would show you them constructive interference, or would make it much louder. And then if you perfectly time sound waves and hit them together out of phase, you can actually create silence. It's kind of an interesting phenomenon. We see that in ocean waves as well. Mixed interference is a little more common, and it gives rise to rogue waves, which are probably more dangerous. Now, if you have waves that are traveling together and you're getting constructive interference, you'll just see very large waves. Destructive, you'll see it begins to flatten out. The problem with mixed interference is that we get these very complex patterns, and it can seem as if you get very large waves that come out of nowhere, which is basically what a rogue wave is. This is the figure I was telling you about, 8.14, I believe, in the book. And over here, you can see that we have, we're adding together two waves in phase. And notice the height, a little bit taller here than it is here. And then we have destructive, where you get, they come together. Notice it's not in a line, okay? And we're lining up here. And what we get, let's try that again. In this one, we are lining up, we get the trough to the crest here, and the trough to the crest there. And we get a flatten out pattern. Is it always perfectly flat like this one? Not really. And then the big scary, which gives rise to rogue waves. The fact that this is drawn in a set of three is not a mistake. Rogue waves typically form in sets of three. In box 8.1, which I believe is in all versions of the book, we get to hear about rogue waves. So remember, the average size of an ocean wave is about 2 meters, right? Rogue waves can be significantly bigger. And what that means is in a typical sea, you can suddenly get a wave, instead of being 6 feet tall, it's 60 feet tall. And this gives rise, so rogue waves are bigger than usual. We begin to define waves as super waves based on it's 1 out of every 23 waves to be twice as high as normal. For 1 out of every 1,155, and this is a logarithm exponential growth. 3 times its height, so that would be about 18. And very, very rarely we get these monstrous super waves, 1 in billions. And that's why they're less common. Now, on the other hand, how many waves are there in the ocean? Every day there are probably billions of ocean waves, which means every day somewhere on the planet a rogue wave is occurring, maybe multiple times a day. And these can have disastrous consequences for ships. We've had many, many ships go missing. There's some statements that the nature of the Caribbean Sea and nature of the Caribbean Sea is what gives rise to these rogue waves around the southeastern United States and between Bermuda, and that's why we have the area where we have a lot of disappearance of ships. One of the problems is, even with all our satellites and all our ability to measure waves, we can't actually predict rogue waves. So this is a real problem. The next video, I'm going to set it up as it's going, is in a wave tank, and it sets up a normal wave pattern. You can see each crest of each wave coming, and we see the little Lego pirate ship man. And as the waves go by, they're all about the same height, and the ship begins to straighten out as they do, just like the Ramapo. What they do at the back of the wave tank at this point is they create a wave that has a different wavelength, wave height, and period. It's actually traveling much faster than these other waves, and this can happen. And when it catches up to these other waves, what it's about to do, you suddenly get, proportional to the ship, a much larger wave. As a matter of fact, if you play this again and watch it again, you'll see you actually get 3. That's because rogue waves tend to occur in 3. The middle one being the biggest one. All right, so we're going to stop with 8.4 there, kind of a short one tonight, and we'll pick up where the next starts with surf cell.